Okay, 7.3, last lesson of our unit, solving exponential functions. Rewrite each of the following with a base of 2. So this is review, this is startup. We're going to apply all these wonderful laws of exponents. Do you remember them, right? This is super important for not only this lesson and this unit, but also the following lesson and unit on logarithms, which is right after this, right? So these are all your laws of exponents. The expectation is you know how to apply these, right? You know all the laws. So let's do a couple of examples. Rewrite each of the following with a base of 2. So remember in an exponent, right? So if I have an exponent x to the m, the x is your base. This is your exponent. Okay, the entire thing. This is your power. That's why when I say something like this, I don't say 2 to the power of 3 because power means something very specific in mathematics. So I don't say 2 to the power of 3. I say 2 exponent 3 or 2 raised to the third, okay, or 2 cubed. Okay, I as a habit don't use the word power, okay, because power means this entire thing, the base and the exponent. Okay, that aside, so let's rewrite this with a base of 2. So 32, if remember, it's 2 times 2 times 2 times 2 times 2. There's 5 of them, so it's 2 exponent 5, or 2 to the 5th. 16 to the 3rd, well, 16 to the 3rd I can rewrite as 2 to the 4th, and that's to the 3rd. Let's use the power rule. 2 to the 4th raised to the 3rd, that's 2 to the 4th times 3, that's 2 to the 12th. Okay, what about a radical? Okay, so we have to remember this particular rule here. Okay, how do we go from a radical form to an exponent that's a rational exponent? So a rational exponent, right, can be represented, the exponent can be represented in the form a divided by b, where a and b are integers, okay, and b is not 0. Okay, so 16, the cube root of 16, well, let me rewrite that as the cube root of 2 to the 4th. And then following our format here on changing from a radical to a rational exponent, the number in the index becomes the denominator of your rational exponent, and then the exponent of the base becomes the numerator, so 2 to the 4/3. So just to see for yourself, quickly on a calculator, right? Evaluate both statements, and you'll see that they are equivalent, or they're equal, okay? 1 over 64, so that's 1 over 2 to the 6th, all to the 1/3. Well, this one, I'm just going to put it all in one fraction there, right? Because that's just a 1. It's not going to affect the value there. So 1 over 2 is like saying 2 to the negative 1. Remember our negative exponent rule? And then all these nested exponents. Okay, I have 2 to the negative 6 to the 1/3. And negative 6 times 1/3 is 2 to the negative 2. Okay, simplify the following by converting each term to a common base. So this is a key idea here when we move into solving actual equations and functions, but let's first understand how do I make this into common bases, okay, and then applying our exponent laws, this time with exponents that are with variables. Okay, letter A, I can rewrite that as 2 to the 6th to the 3x plus 1 divided by 2 to the 3rd to the 5x minus 3 times 2 to the 4th to the 2x plus 5. Okay, let me use the power rule. I'm going to multiply the exponents. When it's an exponent of an exponent, you multiply. So that's 18x plus 6 divided by 2 to the 15x minus 9 times 2 to the 8x plus 20 Okay, product rule. When we have the same base, and we're dividing, we subtract the exponent. So let's do this. Order of operations, I'm going to do the division first, then I'll do the multiplication last. I'm going to combine the base, and then I subtract the exponent. So I'll show that in this step. This is only when I have the same base. Okay, that is 2 to the 3x minus the negative 9, that's plus 9. So that's 3x plus 15 times 2 to the 8x plus 20. I am multiplying this time. I have the same base. I'm going to add the exponents. So combine the base, add the exponents. So that's 2 to the 11x plus 35. Okay, next one. This first term I'm going to rewrite as 3 cubed to the 1/3. And then this radical, I'm going to keep it as a radical now, and I'm going to rewrite it as 3 to the 4th. And then the entire thing squared. Okay. Next one, let's evaluate these two exponents. So that's 3 times. Let's turn this second term here into an exponent. Okay, so that's 3 to the 4/3 squared. That's 3 times 3 to the 8/3. Let me rewrite this as 3 to the 3/3 times 3 to the 8/3. When I'm multiplying, right, I have the same base, I combine the base, and I add the exponents. Okay, so I get 3 to the 11/3. Next page. Okay, solving exponential equations with a common base. Here are the instructions. We'll go over a bunch of examples. An exponential equation is an equation where the variable is in the exponent. To solve an equation where the variable is in the exponent, write each side of the equation in the same base. If necessary, use exponent law so that each side of the equation contains only one base. State the exponents on each side of the equation. Determine the value of the variable. Okay. First one. So let's rewrite. Step one is write each side of the equation in the same base. That's the key here. So that is 1/2 cubed to the 2x plus 4 equals 2 squared to the 5x minus 2. Okay, this is 2 to the negative 3 to the 2x plus 4 equals, let's multiply that out. So 2 to the, let me just simplify it, 2 to the 10x minus 4. Okay, 2 to the negative 6x minus 12 equals 2 to the 10x minus 4. Same basis, I can set the exponents equal to each other and solve for x. And negative 1/2 equals x. Next one, square root of 25 to the 4x equals 125 to the 7x plus 2. So let's rewrite everything with the same base. Okay, so square root of 5 squared is 5, and that's to the 4x equals 5 to the 21x plus 6. Same base, let's set the exponents equal to each other and solve for x. I get negative 17x equals 6, x equals negative 6/17. Okay, we're not going to spend time checking the answers, but I would suggest check solutions on your calculator. Plug in the value of x and then evaluate each side. Okay, check solution on calculator. Okay. Letter C. Let's rewrite. Okay, 3 to the 8x, applying some exponent laws here, so you really have to be conversant with your exponent laws to make this a lot easier. Okay, this is like 3 to the first, right? So when we multiply when we multiply powers, we, with the same base, keep the same base, add the exponents, 8x plus 1. Okay, don't make the mistake of saying this is 8x, right? It's 8x plus 1. We add the exponents. Same base, set the exponents equal to each other, solve for x. Okay, what about this monster here? 64x to the x times x minus 4. So we got to rewrite this. Let's do this. Let's combine that. Okay, this one I'm going to rewrite in terms of, you could do base of 2, but I'm going to do base of 4. This is going to make our calculations or our math steps a lot easier. So that's 4 to the third, x squared minus 4x, 4 squared, 1 minus 2x, and that's 4 squared to the x plus 3. Okay, and then let's use our power rule. So that's 4 to the 3x squared minus 12x divided by 4 to the 2 minus 4x. Okay, and then on the right side. Okay, let's combine the numerator and denominator. I have the same power. I'm going to use the quotient rule. So when the bases are the same, so I have a base of 4, I can combine the base. And when we're dividing powers, I'll combine the exponents by subtracting. So that's 3x squared minus 12x minus 2 minus 4x equals 4 to the 2x plus 6. Okay, solving exponential equations. I have the same base. I have the same base. I can set the exponents equal to each other. And then solve for x. So I have a standard quadratic here. Let me combine terms, simplify, and factor. Next page. Okay, this is the problem we run into sometimes with exponential equations, is that we don't have a common base. So exponential equations that have terms with bases that you cannot rewrite using a common base can be solved approximately. Okay, so for this unit, we're just going to solve it approximately, but we're not going to be satisfied with it. And we'll figure out how to do it exactly in the next unit using logarithms. Okay, but for now, this is a good trial and error method. You can use either of the following methods. Use systematic trial. First, substitute a reasonable estimate for the solution into the equation, evaluate the result, and adjust the next estimate according to whether the result is too high or too low. Repeat this process until the sides of the equation are approximately equal. This is trial and error. It might take a lot of trial and error. You'll see from our work here. Number 2, much quicker, graph the functions that correspond to the expressions on each side of the equal sign, and then identify the value of x at the point of intersection or graph as a single function and find the x-intercept. Okay. Let's do method 1. Systematic trial. Okay, so we are literally doing this. So if this is 5 to the t minus 2 equals 4 to the t, what's a value of t that will make the what's the value of t that will make both sides of the equation equal? So if I just start with t equals 1, right, what happens? That's 5 to the negative 1. I'll do this question mark 4 to the 1. If I evaluate, that's 0.2. Oh, not equal to 4. Okay. All right. You have to start at a certain point and then work your way up or down and see what happens with our trend. Okay, so if I just go t equals 2, well, let's see. That's 5 to the 0. Does that equal 4 to the, 2? Okay, 1 obviously does not equal 16. Okay, I have 0.2 and 4, and I have 1 over 16. Okay, so if you do 4 divided by 0.2, I get 20. If I do 16 divided by 1, I get 16. The ratios are getting smaller. This tells me that we're getting closer to the our answer, right? To our approximation of the answer. Okay, so um, I'm gonna go. Let's jump to t equals 10. Oh no, let me do t equals 3. So we're gonna ask, is 5 to the 1 equal to 4 to the 3? Well, 5 does not equal 64. Okay, but we're getting closer. So 64 divided by 5, that ratio is 12.8. So you can see we're getting closer and closer. The two numbers, as they get closer and closer, right, the ratio we're looking for is 1, approximately, right? So we can keep going t equals 4, t equals 5, t equals 6. That's going to take a while. So let's do a couple of jumps. I'm going to go t equals 10. What happens when I do t equals 10? So that's 5 to the 8. Does that equal 4 to the 10? And that's 390,625. Well, that definitely does not equal 1,048,576. And the ratio of those two numbers we're getting closer is about 2.6, right? So we're definitely shrinking that ratio. So when I did this on my paper, I did a lot of examples. I'm gonna shorten it a little bit. I went to t equals 20, and then you get something like this: 5 to the 18th. Does that equal 4 to the 20th? Well, I can write out this big, so this is what I get: 3.81. I have to start using scientific notation. That does not equal 1.10 times 10 to the 12th. But what's the ratio? Okay, if we're doing the do that ratio, 4 to the 20th divided by 5 to the 18th. Okay, I get 0.28. So we've gone too far, right? We were going down, we're approaching 1. But then we went below 1. So this is less than 1. So we've gone too far, right? So 20 is too far, too high. We need to go back down. So if you keep doing this, go to 19, t equals 19, t equals 18, t equals 17, t equals 16, 15, 14. I get all the way down to So t equals 19 dot dot dot. I get all the way down to t equals 14. This is the closest I can get with a whole number t value. Okay, so t equals 14, 5 to the 12th. Does that equal 4 to the 14th? Well, that's 2.44 times 10 to the 8th. Well, that does not equal 2.68 times 10 to the 8th, but that is pretty darn close. Let's do the ratio. What do we get? 4 to the 14th. 4 to the 14th divided by 5 to the 12th. 4 to the 14th divided by 5 to the 12th. Super close, folks. That's a ratio of about 1.0995, so we are close. Okay, so I'm going to call it the solution approximately t equals 14. Okay, graphically. So if I graph y1 equals 5 to the x minus 2 and y2 equals 4 to the x, okay, and then my window is 11, 15, 1, and 0, 7.5 times 10 to the 8th, and 1 times 10 to the 8th for my y values. Okay, the y values have to be super huge because remember, we're looking for the intersection points of these two graphs. Okay, so what do I get? Here we go. So here's the sketch of my drawing. Okay, I get two graphs that look like something like this. Okay, and then I get my intersection point here. If you grab that intersection point, that's roughly 14.42 and 4.84 times 10 to the 8th. Okay, and we're looking for this t value. So t equals 14.42. And that was close to what I did with my step 1 approximation of t equals 14. Okay, that is a lot of work, folks. Here's the beauty of our next unit. So this is not for this unit, but for next unit. We can solve this using a thing called logarithms, which is the inverse of an exponent. Okay, and that's the beauty of a logarithm, is that this was discovered or invented for this very purpose. Okay, also to represent very large numbers on a scale, like in a graph, in a more readable fashion, but also it's kind of like the anti-exponent. It inverses, right? So logarithmic example, and this is just for your info. This will be a next unit thing, but I just want to show you how we can use this process to make it much easier. Okay, not required for the unit test and quiz for this lesson, but this is just to illustrate. So I have this as my starting exponential equation. I want to take the logarithm of both sides, right? So we're using the basic rules of equation solving, is that what I do to one side, I'm going to do to the other. So when I take the logarithm of both sides, I use this notation called log. What I do to one side, I do to the other. Okay? Property of logarithm. So if you took my course, Math 20-1, I might have shown you when we did the geometric and arithmetic sequence and series. Remember that unit? There's a couple problems where I showed you can use the trial and error method, where you make the bases equal to find the exponent value, or you can use logarithm. Remember I briefly showed you that logarithm method? Maybe, maybe not. Okay, this is very similar to it. So for a logarithm, the property, I can bring the exponent down, and now it looks like a coefficient, and I'm left with log base 10 of 5. And same thing here, bring the exponent down as a coefficient, log base 4. Okay, log base 5, log base 4. So what I can do here is I'm going to divide both sides by t, and divide both sides by log base of 5. So just a little equation rearranging. Okay, to make this simpler, I'm going to say let a equals this entire logarithmic expression. Okay, this is just a number. Okay, so it's a real number, but it's just a number. So I'm just going to let it equal a, and then it'll make our equation solving a lot easier. Okay, so I'm going to cross multiply, and then let's rearrange our equation like this. T times 1 minus a minus 2 equals 0. Let's solve for t. Okay, and then let's plug in back for a. Okay, you can use your calculator and evaluate 2 divided by this entire denominator, and you'll get a t value, I'm going to round it, of 14.43. And let's take a look. Pretty darn close, right? There we go. That's the beauty of logarithms. Again, this is next unit, so don't worry about it for this unit, but this is just to illustrate there is an algebraic way to solve this.